So today we're going to talk about the effective population size. So up until now we've talked a lot about population size, but we haven't really mentioned that we're not actually talking about the census size or the absolute number of individuals. In genetics, the relevant population size is not the census size, but instead it's the number of individuals that contribute to future generations. And this is often much smaller than the population size. So here you can see that maybe only 4 of these ladybugs actually contribute to future generations. And this is called the effective population size. And this is what's really important for all these genetic processes that we're talking about. So there are many situations where apparently large, safe populations are actually genetically threatened. So for example, many populations fluctuate wildly in size, and it's the minimum size that's most important when you're talking about genetic processes. And most populations have individuals past reproductive age or that are too old to mate, and individuals that are juveniles or too young to mate. And these individuals should not be counted in the reproductive population size. And also, when you look at reproductive individuals, their contribution to the population can vary depending on their mating behavior. So think of the contribution of the monogamous dik-dik over here on the left, which has very few offspring, versus a male Guinea baboon over here on the right, which has a harem of females and therefore many offspring. So we have to define precisely what we mean by population size. And the definition for effective population size is the size of an ideal population that loses genetic diversity at the same rate as the observed population. And if you want to think about it, a good way to think about this would be to think of it as the number of individuals that contribute to the next generation from a genetic perspective. But we're going to go back to this original definition because when we talk about effective population size, we need to compare it. Essentially what we're doing is we're comparing it to this idealized population. And based on this idealized population, we're seeing how the population of interest that we're looking at compares to the ideal. And in this ideal population, you would have a constant number of breeders, meaning you would have no fluctuation in population size. There would be a random variation in family sizes. There would be equal sex ratios, distinct non-overlapping generations, no migration, all adults would be potential breeders, there'd be random mating, no selection, and no mutation. And the 3 that are orange are highlighted because these are the ones that are most important, that are really going to affect the effective population size. And also they're also in order, so it's a constant number of breeders. So if there's fluctuating populations, that's going to most impact population size. And then random variation in family sizes will then influence effective population size a little bit less, and equal sex ratios or unequal sex ratios will affect effective population size a little bit less. So in practice, the effective size of a population is usually much less than the number of breeding adults and much less than the census size, because real populations deviate from this ideal. So if we know nothing else about a population at all, and we just know the census size, a pretty good rule of thumb for trying to figure out what the effective population size would be is that the effective population size is about 10% of the census size. So you can use this if you know nothing else about the population. So for example, if we have a census size of 250, then the estimated effective population size would be what? It would be 25. And so the implication of this is that the long-term effective population sizes are only about 1/10 of the actual size of the populations. This is also important. This is the NE to NC ratio. So if this ratio is less than 1, it means that the effective population size is much less than the census size. So if you have 0.04, that would mean that only 4% of the census size is actually represented in the effective population size. And then if you have greater than 1, this is telling you that the effective population size is actually greater than the census size. And this actually really rarely happens in the wild. However, there are certain instances where you could have this ratio greater than 1, and you have more individuals contributing to future generations than the actual census size. And that would be something like if you had migration, really recent migration of lots of individuals coming in and they reproduced, then you would have this ratio would be greater than 1. So one example is the threatened winter run of the Chinook salmon in the Sacramento River, where there's estimated to be 2,000 adults, so that's the census size. And then the effective population size was actually estimated to be 85 individuals. So if we look at the NENT ratio, that's 85 divided by 2,000, and that's 0.04. And that means that the effective population is only 4% of the census population, so it's pretty small. So now we're going to talk about the factors that can influence effective population size, and these things generally reduce the effective population size. And one of these, one of the most important ones, is having fluctuations in population size. And this figure is a very famous figure of the hare and lynx populations over time. And this is a predator-prey relationship where the prey increases and then there's a lag, and then the predator increases, and because of that, the prey drop off, and then the prey increase, et cetera, et cetera, et cetera. So it's a cyclic cycle. But you can see here that over time, there are these really peaks and these troughs where there's a lot of individuals, and then there's an area where there's all this time where there's not a lot of individuals. And if you were measuring the effective population size, how would you do that? Well, first thing you might think is, well, you would do the average. So you would look at the average just straight down the middle. Maybe that's the effective population size. But it turns out that that's not actually really accurate. A better way to measure the effective population size is to look at the harmonic mean of a population. And so this is actually the smallest possible mean. And this would be here, it would be something closer to that. And so you can see that the harmonic mean is actually much more related to the smallest number of individuals over time, rather than the mean or the highest number. And when you calculate the harmonic mean, it's calculated using the reciprocals. So the equation that you would use is this. It would be the effective population size is T, or generations, over the sum of 1 over N, or the census population size. So let's do an example of this. This is an example of the northern elephant seal, and it's prized for oil made from their blubber, and it was hunted to extinction through the 1800s until a Smithsonian expedition found a remnant population on Guadalupe Island off the coast of Baja, Mexico, and then proceeded to kill all but a few for their collection. But luckily, the seals managed to survive and were protected by the Mexican government in 1922. And they've actually since recovered to over 100,000. So we're going to calculate their effective population size. So for simplicity, we're going to assume the population went from 175,000 to 20 to 175,000 individuals over 3 generations. So we would take this and we would plug and chug. So 3 generations, that's going to be our T on top. And then we have 1 over 175 plus the 1 over 120, and then the 1 over 175,000. And then that equals a effective population size of 60 individuals. And you can see that effective population size of 60 individuals is much closer to this minimum size right here of 20 than it is to the mean over all 3 of these, which would be 116,673. So another factor that is important in effective population size is the variation in family size, and this can have a big influence on effective population size. So family size is the lifetime production of offspring per individual, and in that ideal population, there's an expected variance of 2, meaning all individuals contribute to offspring all the time. Now, in the wild, this is rarely the case, that there's this even number of offspring produced by every individual. And this is the equation that we're going to use to calculate this. So you would calculate effective population size, and that's 4n of the population minus 2 over vk, which is the variance in the family size, plus 2. So here's an example. This is the Asiatic lion, And in captivity, they have an average family size of 1.65, but a variance in family size of 32.65. Perhaps what's going on here is that when you have breeding programs, you have one male that's being mated with many females, and so that one male has many offspring, whereas some of the females never mate. And then let's also say that there is a total population of 200. So we put these into the equation. So we have 4 times 200, the n minus 2, and then we take the variance here and put that here, and then that turns into 34.6, an effective population size. So variation in family size is also relevant to when you're talking about fish and hatcheries, and this creates something called the Ryman-Laker effect. So in hatcheries, by supplementing wild populations, it increases the total number of adults, but it actually decreases the effective population size. And this is because offspring from a few adults with higher survival increase the variance in family size, or that BK. And the reason for this is because in a hatchery, you often have just a few individuals that are then producing many, many offspring. And then those offspring get released into the wild, and those offsprings are often larger. You can see here in this picture that a hatchery steelhead on top and a wild steelhead on the bottom, they're larger, and then they outcompete the wild counterparts and for resources, and then they end up having offspring themselves. So you end up getting this very big variance in family sizes, which then can ultimately reduce the effective population size. So there's a trade-off. So by supplementing and increasing the ability for recreation, you're actually reducing the genetic diversity of the population. And it is possible to find a sweet spot where you are supplementing the wild population somewhat, but not enough to actually throw off the effective population size. So that stocking needs to be a smaller number than the actual wild individuals and the actual effective population size out there. And then it will be okay, because you'll increase some of the adults, but you'll be maintaining that genetic diversity. And this is also relevant when you're talking about captive individuals at places like a zoo. And the way that it's best to maintain a little variation in family size so that you don't kind of skew this effective population size in these captive individuals is to try to keep the NE to NC ratio in captive populations about 1, meaning all individuals contribute equally to the number of offspring. And if you do that, then you should be able to maintain that effective population size over time. Unequal sex ratio is another factor that can reduce the effective population size. Sex ratios in reproductive adults often deviate from equality in wild populations. Typically in mammals, there's an excess of females because many mammals have harems where one male is the leader and mates with many females, like in these baboons. And in birds, there's often a deficiency of females and an increase in males. And this species is the Jacana bird, and this is one example where it is the opposite, where you have one female that mates with many males, and that female is larger and defends territories, and so there's difference in the sex ratio. And so the equation that you use to estimate effective population size is this. So you do 4 times the number of females times the number of males over the number of females times the number of males. So when you use this equation and you plug these numbers in, you take this 4 times the number of females, 605, times 6 males, and then you add those up, and you get an effective population size of 24. When you look at the NE-NC ratio, that is 0.04, meaning that the effective population size is only 4% of the census size. And when we also think about unequal sex ratio, it's important to talk about climate change. And how is this relevant? Well, this might actually be distorting sex ratios in some organisms. Think about turtles and crocodiles and other reptiles where sex is determined by the incubation temperature. So by increasing the temperature, you may actually skewing sex ratios, which could reduce the effective population size and threaten these species. So now I want to talk a little bit about the relationship of effective population size and heterozygosity, and specifically the loss of heterozygosity over time. So equation that is relevant is this. It's heterozygosity at generation T. And there's 2 important things I want to talk about. One is that the time scale of loss depends on generations t. And I kind of glossed over this earlier, but I want to make a good point here that when we're talking about in genetics, we talk about t, we're talking about time, but when we talk about time, we're talking about generations. And the reason we don't use years, for example, is because years mean different things in different organisms. So, for example, 102 years may be only 1 or 1.5 generation for an elephant, but it might be 60 or 70 generations for a mouse. So that's why we always calculate time in generations. So heterozygosity is dependent on this generation time. And when we look at this equation, if we take this HO and we move it around and put it on the other side, we end up looking at the rate of the change in heterozygosity, and then we can calculate that, so the change in heterozygosity. And another important thing I want to mention is that this rate, or this change in heterozygosity, depends on the effective population size here, not the census population size. Okay, so let's do an equation. If we have an effective population size of 500, how much heterozygosity will be lost in 500 generations? So here we take this equation, 1 over 2 times 500 is our effective population size, 50 generations we put here, and we end up getting heterozygosity of 0.95. So that means 5% of the heterozygosity was lost in that 50 generations. Now what happens when we have a much smaller effective population size? If we have an effective population size of 25, how much heterozygosity will be lost in 50 generations? So we do this again. The only thing we change is the effective population size here, and we do the math and find out that here we have 0.36, which means we have a loss in heterozygosity of 64%. So again, when you reduce that effective population size, you really lose a lot of heterozygosity. So the last equation I want to talk about is a really interesting equation, important equation, that is going to help us figure out a target effective population size. And this is just rearranging this previous equation here. And we talk a little bit about it. Its target effective population size depends on t, this rate of heterozygosity loss, and then 2 times the natural log. So this is when we want to calculate the minimum population size needed. And here's an example. We have the eastern barred bandicoot, which is a highly threatened marsupial in Australia. And the question is, what is the minimum population size needed in the wild so that genetic diversity is not lowered more than 10% over the next 50 years? And then we have given 2 other pieces of information, that the generation time is 1.5 years, and that NE/NC ratio is 0.13, meaning that the effective population size is 13% of the census size. So let's move this up so we get a little more space. And we'll start trying to figure out this equation. So first we need to figure out how many generations is it. So we take the 50 years given to us and divide it by that generation time. We get that there's 33 generations that have passed. We put that in the equation. And then the next thing is we want to figure out what this rate of heterozygosity is. And the question is asking so that it doesn't lower it more than 10%. So that means that the rate of heterozygosity is going to be at the minimum 0.9. And we plug that into the equation, 0.9, and then we do the math and we get that a target NE, effective population size, is 159. But that doesn't really tell us much, because we know that the effective population size is not the census population size. So we have to figure this out in terms of what the actual census population size is. So what we do is we use this equation up here and plug in this 158. So we end up getting NC is 158 over 0.135. And that means that we need 1,170 individuals in order to maintain the genetic diversity over this time. Okay, so this is just a summary of all the equations that we used. The first one is the rule of thumb. This is if we have no other information, that we can kind of estimate that the effective population size is 10% of the census size. This is the equation we use when we're looking at fluctuations in population size. This one will tell us about variation in family size. This one will tell us about the effective population size if we have an unequal sex ratio. This tells us about the loss of heterozygosity over time, given the effective population size. And this one talks about getting that target effective population size if we're looking at a loss of heterozygosity over time. All right, that's it.